Hey everybody, Kent Marts here from Explore Scientific. Am I on?
Obviously not. You can keep talking, they can hear you.
Apparently things aren't cameras. Something's going on. Paul's banging on things with his thumbs and index fingers and such. It'll be up here in just a minute. I can understand you hear me.
You're up.
I don't see it on the monitor anywhere, but supposedly almost up here, getting ready. So another quick countdown here. Maybe we'll be up in 3, 2, 1. There we go. Hey everybody. Kent Marts here on Wednesday for Amazon Live warm-up broadcast via our social media platforms. Today we're going to be talking about first light telescopes and how to get started in amateur astronomy. Lots of people have an interest in amateur astronomy, but they don't know where to start. Well, a great place to start is with our First Light Hour, Explore Scientific's First Light series of telescopes. I have here to my left the Explore Scientific First Light series achromatic AR, 80 millimeter by 640 millimeter focal length. What that means is there's 80 millimeter diameter objective glass up here that has two pieces of glass that start focusing the image, and then a focal length of 640 millimeters to where that image comes to focus at the eyepiece. The eyepiece is right here. This telescope comes with everything you need to get started. A 25 millimeter super plossel, a 1 1/4 inch diagonal, which fits into the 1 1/4 inch focuser. And just tighten that down so it's there. Put the eyepiece in. Attach the telescope to this little tripod it comes with. This was a Twilight Nano. It's very simple. Left, right, up, down tripod. Let me see if I can move this a little bit over, get more of it in camera range here. A simple left, right, up and down tripod. Very intuitive, very simple to use. Great way to get started. You can actually see the glass down in there. There you go. See the glass shining off on the, with the lights, the studio lights. There you go. There you go. You can see the glass in there, right there. This is a great telescope. Does not have a massive amount of magnification. People crave massive magnification. The problem is that makes it really hard to focus, really hard to point, and really hard to keep things in the eyepiece. That's why we ship this with a 25 millimeter eyepiece. Not a huge amount of magnification. Makes it easier to find things in the eyepiece of your First Light telescope.
Now,
Paul's got a question, had a question, forgot his question.
well, this telescope, right, it only takes certain eyepieces, correct?
That's 1 1/4 inch eyepiece. So generally there's two sizes of eyepieces, 1 1/4 and 2 inch, meaning they're 1 1/4 inch in diameter or 2 inches in diameter, so that'd be yay big around, not this big around. There's a third one out there that's like 0.986 of an inch, so smaller than 1 inch in diameter. Those tend to come on very small, really basic beginner and educational and toy telescopes. They will not fit on this telescope because they're too small, right? So they won't fit on it. That answer your question, Paul?
I just wanted to make sure that we cover the basics.
Good. So my monitor's turned really far sideways, so I can't see it. We'll deal with that here. I don't want to step off camera. So this tripod raises up higher than this, but we have it set this way so it looks good. Good positioning on the studio. Hey, Paul.
Don't move it.
Nah.
Oh my gosh. Complain about something. You don't want
No, there's an observation, not a complaint. So, one word of caution, it comes in various places. This little thing says in like 19 different languages, don't look at the sun with a telescope. Why? Because you'll burn your eyeball, and that will be very, very, very bad because you can't fix it. You're always going to have a burned eyeball from looking at the sun. Now, there's ways to safely look at the sun. We'll talk about that here in a minute. Offerade says that looks like a 45-degree diagonal. Nope, it's a 90. Here we go. Turn it sideways, and you can see right here that goes. Turn it a little bit better. You can see it right there. So it's a 90 degree diagonal. That diagonal is just a mirror, is all it is, set the mirror is at a 45-degree angle. It allows you to look down at 90 degrees, right? If it was a 45-degree, the eyepiece would be about right here, and the mirror would be set at 22.5 degrees, so you could get that 45-degree angle. 22.5 is, yes, 22.5 degrees, half of 45. So what this does is, if you're looking at something on the horizon, looking into an eyepiece, and there are some telescopes that do this, and you could do this with this one, put the eyepiece here, and you might be able to get it into focus, right? Which is all well and good if you're looking at something out there on the horizon, right? But if you start trying to look at things up in the sky, the higher it gets, if you're going to look at something like you want to go out and look at Vega tonight, this is almost an impossible position. As you can see, the eyepiece is not on the screen, but you get the point. The eyepiece is so low, you can't really get to it. So that's why we use a diagonal. It goes in there, we can tighten it down, we can find a comfortable position to look at, and if we're looking at something in the sky that's high up, it's a lot easier to see into the eyepiece because you're looking down into it, not having to look up through it. It was a trick of the camera. Yes, I can see that. Could be. You get weird angles, and you don't know how it's going to look once the camera starts looking at it. So I'm going to move over here and move this monitor, step off a camera just a second, so I don't have to keep craning my neck to see my monitor and see the questions pop up. A nice, lightweight but yet sturdy tripod is the telescope mounts to it. How do you mount the telescope to it? It's real easy. It's going to come, you just unscrew that screw, and telescope slides right off. Now, I tell people, you start turning that knob, you want to make sure you have a hold of it really well, because you don't want it to fall off and hit the ground, right? One other thing it comes with, and I don't know if we're going to take it off so you can see it. It comes with, right here, a red dot finder. That red dot finder is what you use to locate, right? The red dot finder is what you use to locate objects in the sky. How do you do that? Well, if you just stick the red dot finder on, and it does come off, if you want to store it, put it back in the box it came in, right here, right? So you can put it back on, tighten down the set screw, it's on. If you stick it on there, the red dot that shows up in here is not aligned with where the telescope looks at. It can be off, left, right, up, or down. So you turn it on, and how you're going to do it is you're going to put it on the mount, the tripod, and tighten down the bolt that keeps it in place. And now you're going to move the telescope and point at something that's distant. The manual says, I believe, 300 yards. That's the probably lowest minimum distance you can do it. But if you can find something that's a couple thousand yards or even miles away, I always say miles are better than yards, and yards are better than feet, right?
If you're going to miles, though, you probably need, because I was doing this earlier.
Mm-hmm.
And just, to prove what's going on. And what I found was that you probably need like a 14 to go if you're out of a mile. To be able to.
A 14 what?
14 millimeter eyepiece.
Well, look. Look. With the,
what I had a 25.
I've done it.
Could not get it exactly in the middle.
No, but you do the best. You do the best you can. You do the best you can with what you got.
Well, you're going to need a bigger eyepiece.
And we'll talk about that here in a minute. It's a good point, Paul. So you can. But what you're going to do is,
I guess it matters that my
Paul went to a
microphone
place
wasn't
where he
even
could see
on.
a cell phone tower half a mile away, something like that.
3/4 of a mile.
3/4 of a mile away. And what you do is you put an obvious point of it, a unique, a light that you can see at the very top, or
It's got a blinky
one of
light
the
on it.
antennas. And you use it using something on land because, look, you've got to move the telescope to find it. So you know it's over there, and you just simply move the telescope looking through the eyepiece until you find it, and then you go up the tower, whatever, the tree, whatever, until you get to the unique part. You're going to use a broken branch sticking out of the very top. There's a tree line, there's a taller tree, and you use the top of the taller tree or the top of the cell phone tower. Once you get centered up in the eyepiece as best you can, you simply turn on the red dot finder and look through the red dot finder and move. There's two little knobs. You move them, and the red dot will move left, right, and up and down until you get that red dot on top of the cell phone tower. Now, you don't want to just go on down the road and start viewing, because you want to look through the telescope, because it's very possible you move the telescope a wee bit, right?
Oh, I kept moving it constantly.
Yeah, and so you want to get it centered up, look through the red dot, center it up, look through the red dot until whatever it is in the center of the eyepiece is also covered up by the red dot. Now you're ready to go out at night and look at something in the sky. Say, you want to go out tonight and look at the super, what are they calling it? Anyway, there's a supermoon. It's 13 or 14% larger.
You got K2 as well
than average. It's going to be 30% brighter than other full moons, but 13% larger. Most people can't tell the difference by naked eye. But hey, it's popular, and people are going to go do it. And I'm going to tell you that a 30% brighter moon through a telescope is going to be really bright in the telescope, because it's really bright in the telescope when it's normal brightness, right? All right. Osmosis 007, howdy y'all. And Tariq, howdy. Tariq says, hi, Paul and Kent. Osmosis says, in Iowa, we use the wind turbines. Oh, absolutely. If you're out where there's a lot of the gigantic electric generating wind turbines, you can do it. You also, where you're in very flat country with not a lot of trees, you can see things a long ways off. Looks like you had a what is that? 102? Yeah. That's it's an AR 102.
No, it's an ED 102.
It's an Essential Series 102 out in front of our building on a MAZ 01 tripod. That is a combination you could order today off of the Explore Scientific website.
It takes 3 extension tubes to get that to get in focus.
Because you're so close.
3/4 mile.
Yeah, because you're so close. It also, if you look closely, has a straight-through finder scope. I think they're like $89 on the website. Has a straight-through finder scope as well. It's an upgrade from the red dot finders. The red dot finders are an entry-level item, easy to use. I've used them for years. They work great.
I'm making sure I use one heck of an eyepiece, though.
What, did you focus on the camera? Did you focus that thing? Looks almost out of focus or not sharp.
Well, it's because I'm zoomed in.
Yeah. What did you use?
Just my iPhone.
Oh,
just
okay.
Snap.
Right, just
see,
use
it's actually a video, see?
Yeah. So there we go. So same process. That mount is the MAZ 01, the Twilight 1 mount. Has slow motion controls on it. That we'll look at another one, an equatorial mount that has slow motion controls, but works the same way.
I wanted that one because I didn't have to wait or anything like that. I just go on.
Wanted to go play with it. And,
I'm going to take it. That's what I'm taking home tonight. I'm going to point it at the sky, show some kids.
I would not look at the full moon with that, Paul.
I'm going to look.
Without getting, if you're going to do it, get a neutral density filter to put on it to cut down some of the brightness.
I don't have one,
no,
there.
We have them here.
Well, is there one? You'll have to give it to me, Ken.
Yeah, we can check out a neutral density filter.
The expert.
Nope, you're not. Nor am I, but I know
I
a little
love that
bit.
Eyepiece. Whenever I use a telescope from here, and I'm lucky because I get to use whatever I want. Because here we get to use whatever we want. Yeah. That eyepiece, I took it from back there behind you, off the set. Mm-hmm. It's a 2500 degree, I think it is.
Big 2-inch eyepiece.
It's so nice.
We have some 2-inch. Those 100-degree eyepieces in the 92 and the 82s are all nice. The 82s are generally our best-selling line, although we sell a lot of the 52s. And that's a good segue, Paul, into talking about eyepieces. The telescopes come with an eyepiece, in this case a 25 millimeter superplossel. How that works is, let's talk about eyepieces and such. First, eyepieces are one component of magnification. The other component is focal length. So it'd be the focal length, in this case 640 millimeters of focal length, divided by the focal length of the eyepiece. That's the number printed on the side of the eyepiece, 25. So 25 will yield a magnification of, what did I say, 640. 25 will go into 600, 24 times. So it'll be 25 power, almost 26 power is what you'll get. So whatever you see is going to be, is that right? That math's right, isn't it?
I have no idea.
4 will go into 100 4 times. It'll go into 600 24 times. It's a 25, so that's 26 times. And it's almost 650. So yeah, it might as well be 26 power. So anyway, focal length divided by the focal length of the eyepiece. Interestingly enough, if it's a microscope, it's not division, it's multiplication. It works the same way. Focal length times the focal length of the eyepiece yields the magnification of a microscope. It's multiplication. Telescopes are division. So if you want to, one of the first upgrades many people make to a first light telescope is buying eyepieces. And we offer the 52-degree waterproof eyepieces from the same engineering, same design, same everything as our more expensive eyepieces. The 52-degree are our least expensive eyepieces. They're, as I said, waterproof. They're argon purged. So as they're made, they're assembled and then set in 1 meter of water for, I believe, 30 minutes, and then checked for leaks. And if they pass that test, they get shipped out to you, the customer. It's a pretty cool process. I've seen videos of it. So they use argon because argon is a inert, hydrophobic, in other words, doesn't like water or moisture. It's a dry gas. So if you replace all the air with argon, guess what? There's no moisture, and it can't hold any moisture, and therefore your eyepiece can't fog up internally. They'll still fog up with dew on the outside, on the glass, or somewhere else, but they will not fog up internally. Mateus Volkovas. Hello, does Vixen eyepieces are good for beginners? That becomes a budgetary question. Vixen eyepieces are great eyepieces. They can be pretty expensive. So that becomes a budget question. They're good eyepieces. You can spend as much money as you want in astronomy pretty well. But if you're just starting out, don't get hung up on super expensive gear. You work your way up to stuff. When I started, I didn't have any expensive gear. I worked my way up and ended up buying a used 8-inch Celestron telescope, and then slowly bought better and better eyepieces and worked my way up. And that's the only telescope. I collected up a couple of Dobsonians and some other telescopes, but this was, then I came to work here and already had a background in astronomy. Really was good to come into the company with the knowledge I had, because it translated very well. Off-rade, 80 millimeter f8 should have less secondary spectrum than the common f5 acromats. That's correct. A little bit longer focal length. Okay, let's talk about acromats and what Off-rade said. A two-lens system, the light comes in, it starts focusing into a point. However, because of refraction, effectively, that second piece of glass becomes like a prism and starts breaking the white light into its constituent elements of blue on one side and red on the other. So when you see a bright object, like a planet or the moon or bright stars, you're going to see a blue fringe or a red fringe, depending on where your eye lands and what part of the spectrum you're seeing. You're going to see a red fringe or a blue fringe or maybe a purple looking fringe, right? That's the white light starting to break up. It's really close to being all white light, but it's really not. It's breaking up into the prisms, and you're seeing the ends of the rainbow, right? Red on one end, blue on the other. You're seeing the ends of the rainbow. A double lens system is called an achromat, and very short focal length telescopes can really start having a lot of chromatic aberration, where it's a bigger and bigger because it's spreading out more. So with longer focal length, it cuts down on that somewhat and gets rid of some of that chromatic aberration. Don't scare you off in this telescope. It's not like you're looking at something and you have this big purple circle around it. You know, chromatic aberration doesn't bother me. Coma, where the stars sort of look like little comets, little smears, that doesn't bother me either because I understand what it is. You know, if you want to not have things like that, you have to spend more money. And that's not what I'm talking about today. I'm talking about getting a good starter telescope that's a solid telescope with a good mount.
Do sometimes get diamonds in the rough, too. So some of these scopes, when they come out, are just fantastic.
They're still going to have chromatic aberration, but some of them
are really good.
Not as bad as some, right? But I use, you know, we sell a lot of these at telescopes, and nobody complains about the chromatic aberration. Oh, I wouldn't say nobody. I could probably go back through the system and find somebody in the past 5 years that has, but
I would, only because I'm like super photographer.
Well, yeah, but then you probably wouldn't spend the money on this telescope. You'd spend.
I'd get a mid-grade at least.
You'd spend $1,000 on an optical tube, not $359 or whatever the price is for this system, right?
If you're not that big, not that picky, and you're just wanting to start out and see if you even want to do it, I mean, you can even start it with a pair of binoculars if you wanted to.
Oh, absolutely. That's a great way to start doing this. That's frankly, with the Mark 1R and Mark 1L and a pair of binoculars, that's how I start astronomy. Osmosis 007. I believe argon gas is a smaller molecule than air and transmits heat much, much slower. It's why they use in high-end windows and high-end high-end eyepieces. Let's see. Argon is a larger molecule than, I'm trying to remember a periodic table. It's smaller than oxygen by 1 proton, maybe? Can't remember. But, you know, helium and hydrogen are the two smallest atoms, and they are significantly smaller than argon. But it does create a vacuum effect, not a vacuum, but argon-filled windows do have a low E transmission, right, in efficiency. And Osmosis 007 says, as a Mac user, field of view doesn't bother me. I'm looking for eyepieces as a new user. It will really nice not getting hung up on mega field of view since I love planetary. Right, so an interesting subject to talk about, field of view. Maxitov Cassegrain and Schmidt-Cassegrain and Maxitov Newtonians all have very long focal lengths generally. That focal length means that with the same, if this is 26 power, right? 26 or 27 power at this focal length.
Cheat.
And you double the focal length to 1740 and use the same eyepiece, you're going to double the magnification to 50, what did I say, 27 to 54, right? So longer focal lengths with the same eyepiece offer more magnification, and that's what Osmosis is getting when you use the Maxitov. They're generally 1400, 1900, some get up to into the 2000 millimeters of focal length. So the same eyepiece, they start offering significantly more magnification than this telescope does. So with that, looking at planets and the moon can be very enjoyable because you're getting larger images of it. Now, one cautionary tale or word of caution, there's some nights the stars are twinkling, right? Well, you put a low power eyepiece on, let's say, Saturn or Jupiter, and they look fantastic and crisp at low power. So you go, man, I'm going to start going high magnification. You start adding magnification. You get to a point where it looks terrible, and people think, oh, my telescope's broken. There's something, it must be the eyepiece. It's not the eyepiece. It's the scene of the sky. You've magnified the scene so much that you're seeing the effect of what's causing the stars to twinkle. Stars twinkle because of different densities of air. So just like, think about the sky as a big pool of water, a swimming pool, and there's no ripples or anything, perfectly still. You can see leaves, toys, everything on the bottom, little tiny stuff. You can see them really well. But if you slap your hand on the water a little bit, it's a lot harder to see. You get 4 or 5 kids, hang on, you get 4 or 5 kids splashing around the pool, you really can't see the bottom of the pool. The sky's the same way. If the stars are twinkling, which is the star, which is a pinpoint, that under perfect conditions doesn't twinkle or move, but as the air changes density, the star moves around, right? Well, if you take the surface, the circle of a planet, there's a star here, well, that density that makes the star do this and this star do this in a different time than that one does is going on all over the surface. At low power, you don't see it, but at high power, you do. So you got to be careful, you know, when you're starting out, understanding that. What you got?
I think the best example that we should do is we should take the camera and put it in the telescope and film the highway just outside of here and show all that heat coming up off the highway, and you will see exactly what you're talking about.
Thing.
And it's the same thing, but since it's so much, you can actually show people what's happening.
Yeah, we should do that on some night when the stars are twinkling real bad. Go show a picture of, and we'll have to wait till this fall when Saturn gets back up and becomes a fall thing. Easier to do in the evening than get up at 4 in the morning to do this, because we get set up as soon as it gets dark we can take pictures. Show Saturn and looking really nice at low power, and then you start jacking up the magnification, and boy, it goes to heck really fast. So, Alfred, this scope seems a good choice for beginners who get into astronomy by media coverage of comets. Remember the comet catcher in the 80s? However, that was a weird scope. I don't remember the comet catcher, but there's plenty of weird scopes out there, and some people love that scope. I'm sure people loved it and didn't think it was weird at all. The coverage of comets, the coverage of moon. There are people who hear about the supermoon and buy a telescope and want to go out, and their first view is going to be looking at the supermoon. It happened when they have the eclipses, you know, lunar eclipses where the blood moons happens. People buy a telescope and they want to go out and use it tonight for the first time, looking at the supermoon, because man, it's a supermoon. I want to see it bigger, and that's all well and good. My strong advice is, if you're interested in astronomy, buy the telescope now and learn how to use it, so when those things come along, you don't have to struggle. You can simply just go do it. For instance,
so Kent,
if you've never
we've got just seconds to go to Amazon. So
Okay.
if you just put yourself on hold for a second,
and
we'll
be
come back and you can finish your thought. Okay?
Jump in with both feet. Hello, everybody. Welcome to Wednesday's Amazon Live broadcast, where we're streaming out there to the world. Woohoo! We're talking today about First Light Chronicles, named after one of the series of telescopes Explore Scientific produces. It's the telescope right here in front of me. It's the First Light AR 8640 on a TN, Twilight Nano Tripod. Let's talk about it real quick. The telescope comes, it'll be disassembled, you put the tripod together, the telescope is going to come, and this is how you put it on. It's real simple. Sorry. It just simply slides on, tighten down that screw, and hand bolt, whatever you want to call it. And there you go. It's attached, and now you're going to have to put on the diagonal, which comes with it. This little doohickey right here. And let me get it down here. Where's the camera at?
I've got both.
This little doohickey right here, the diagonal, and the eyepiece. You're going to simply put the diagonal in there. That diagonal makes it much easier to look into the telescope. Tighten down the tension screw, put in the eyepiece. Get your red dot finder right here and slide it into the obvious slot it goes into. Tighten the screw down. And you're ready to start using this telescope right now, out in the parking lot, in your front yard, or when the supermoon comes up tonight, you can look at it and it's going to be really bright and hurt your eye. Not injure it, but boy, it's going to be bright.
Now, I'm not going to look at the moon. I'm going to look at the comet.
You do have to remember to take the lens cap off, right? That's what you got to do as well. So Paul's going to go out and look at the comet tonight. The problem with that is the full moon is going to make it difficult to see because it's about magnitude 8 point something, which, you know, gets into some real technical stuff we don't need to. 8 something, 9 is dimmer, 10 is dimmer, 11 is dimmer. As you get to
at like
3, 2,
negative
1, 0,
40, right? The moon's like at a negative 40, right?
Yeah, it's something like that. And so it's going to make the sky bright, and if there's a lot of humidity in the air, which there is because it's northwest Arkansas and it's July.
You can still see it.
You know, we were talking at my Astronomy Club meeting last night, Sugar Creek Astronomical Society, that it was difficult to see last week, 2 weeks ago. One of the guys had a go-to telescope, and he found it, but he knew exactly where it was and what star it was next to.
It's the closest it's going to be today.
Yeah, but it's still like 2 astronomical units away. Astronomical units.
It's just a little bit past, like, it's a little further away than Mars.
You need to consult, and it's very small, relatively. You need to consult a good sky chart to be able to find it, but even last week, a master observer, Paul Anderson, said it was it didn't look like a comet. Photographically, they could see a tail when they took pictures of it. You could see a little tail, but this is, you know, I look forward to the day, Paul, when a truly great comet comes by, and you can see it.
Hellbop.
Everybody, you know, Hakatake, you know, back in the 90s, Hellbop was a good one, you know, that you can look up in the sky and go, wow, there's a comet. Anyone can do it. They just have to look up and notice it. It's not like one of these things where you say, okay, see those 2 stars right there? Well, make a right angle triangle. That little thing right there, that's the comet. You know, Comet Neowise, you could see it visually. Barely with binoculars you could see it and know it had a tail, but those aren't great comets. It's been more than 20 years since we've had a really what's called a great comet that has a head and a tail. I can remember 2 comets back in the 60s and 70s, Comet Bennett and Comet West, that was a big bright ball in the sky with a tail that stretched halfway across the sky. I pine for one of those to come by, Paul, because that will excite people. And will get people interested in astronomy, and hopefully not just a flash in the pan. But if you have an interest in astronomy and have never taken the leap into a telescope like this is the way to go. Why? It's simple to use. You just saw me. You set up the tripod, you put the little tray in, you put the telescope on it, you put the red dot on it, put the diagonal in with the eyepiece. Now you're almost ready to use it. What you have to do is take the telescope out in the evening is the best, or under the shade of a tree like Paul was doing a while ago. Well, you weren't using a red dot finder. You're using a
I was
8x50.
Not even under a tree.
Well, yeah, but you weren't using a red dot finder either. You should go out in the evening, before it gets dark, and you want to look at something that's the farthest away thing that you can see. I think the manual says 300 yards away. That's the minimum standard. If you can get half a mile or 2 miles or 5 miles, or maybe you're out in Kansas where you can see 15 miles away, find the thing you can see that's farthest away. Paul was out looking at a cell phone tower that's 3/4 of a mile away roughly. And what you do is, and you pick something that's easy to find, because you can't be surprised how hard it is to point a telescope at something without a aligned finder scope. So what you're going to do is, you're going to move the telescope looking through it until you find the radio tower, and then you're going to go up to the top of the radio tower. Now you're going to turn on the red dot finder and look at the red dot. There's no laser that shoots out. It's just a red dot projected on what amounts to a heads-up display, right? And so you're going to look at that, and you center up on the top of the tower in the eyepiece, and using the red dot finder, you're going to move, there's 2 little knobs, figure out which ones they are. One moves it left or right, one moves it up and down, and you move that red dot until it's pointing, covering up the top of the radio tower. Look in the eyepiece. Chances are you've moved the telescope a little bit. Well, you recenter it, and you keep adjusting the red dot, making sure it's centered. When it's centered and the red dot is on it, you're good to go. You're going to go out tonight, and you're going to say, I want to look at the moon. And you're going to find the moon by looking through the red dot finder this time. Right? You're going to find the moon, and then you're going to look in the eyepiece, and if you've done a good job of getting the alignment right, the moon's going to be in the eyepiece. Now, it may not be centered up. Why? Because it's farther away. And because of parallax, you pointed the red dot to something that's a lot closer. That's why I say if you can get something 10 miles away, that's better than 300 yards, right? And so you pointed at the moon, you got it in the eyepiece, centered up, and now fine-tune the red dot towards even better. Now, as you go on your journey across the sky, you see something you want to look at, you simply just get down, look through the red dot, move the telescope until you get it on the red dot, look in the eyepiece, and there you go. Now, don't forget to turn the red dot off. That way your battery will last for a long time. Or you can do what happens and you forget to turn it off. You say, I'm going to turn it off when I get done using the scope. Well, you get done using the scope, you don't turn it off, you pack your telescope away, you come back 4 weeks later and the battery's dead. Well, now you're frustrated and you got to go buy another 2320 or 3220, flat battery and put it in there. And remember to turn your red dots off, right? This is a great telescope for someone who's just starting out. It has enough objective power. The bigger around, the more light it pulls in and focuses on your eye. It's got enough to get you started and get you going down the road to amateur astronomy. It has enough magnification power to see things slightly magnified more than your eye. By slightly, I mean this is going to be, let's talk about magnification real quick. Magnification is a division process. It's the focal length of the telescope, in this case 640 millimeters, divided by the focal length of the eyepiece. There's a number on here. It's at 25. Comes with the kit. So 4 will go into 100 4 times, and 100 will go into 600 6 times. So 6 times 4 is 24. And so now up to 600 power at 24, but it's 40 more millimeters. It's almost 50. So 24, 25, 26, 26 power, right? So this gives you a magnification of 26 power of what your Mark 1R and Mark 1L eyeball sees. So this is a 26 power magnification. One of the first things some people do is when they get a first light telescope, they'll go buy some of our waterproof eyepieces. Those come in the 52-degree series. This Super Plössl is a 52-degree series eyepiece. However, our waterproof eyepieces have more design to them. This is a Plössl design. Ours is not a Plössl design. Has more glass, better engineering, and they're waterproof. This one is not waterproof. What does that waterproof means? means that all the air inside has been forced out, replaced with argon, an inert, dry gas that won't fog up because there's no moisture inside of it. So it can't get any internal fogging. As long as you don't unscrew the barrel and take the eyepiece apart, the purge is there. I've had people call and say, yeah, I got the eyepiece and I wanted to see what was inside of it, and when I unscrewed the barrel, that would be the silver part right here, they said, I mean, let's come off of this one, no problem. They said there was a psst, and was that a problem? Yeah, you just ruined your eyepiece. It's not waterproof anymore because you destroyed the perch. And I go, oh, okay. So don't be taking things apart that you don't need to, right? All right, so once on the moon, you simply turn the focusing wheels, focus it in and out to where it focuses for your eye, and you can see it sharply and clearly. Now, let's say you're looking at the moon. As the moon's moving across the sky, you're going to have to follow it periodically by moving the telescope left or right and up or down, depending on if it's in the southeast or the southwest, and you just follow it across the sky. You move the telescope while you're looking through the eyepiece. You don't look up here and go, okay, I'm going to move it. You're going to lose it. You look in here, and before the moon gets out of the eyepiece, you move it like that while you're looking at it, and you keep moving across the sky with the moon. Now, so if you want to double the magnification of this telescope, this is a 25, you'd go down to a 12.5 millimeter eyepiece, because if you cut the focal length in half, right, 52 goes into 640, we determined 26 times, right? If you go to a 12.5 will go into 640 millimeters. You cut it in half, so you multiply the 26 by 2, and you find out it's how much? Yes, 52 power. If you cut it down to a 12.5, say go to a 6, you're going to go to 104 power-ish, right? Real close. Not exactly, but really close. All right, so that's how magnification works. When you double the magnification from the 26 to the 12 or 10 or whatever you have, that's all well and good, except now the moon is going to appear to move, or the star you're looking at, or the nebula is going to appear to move twice as fast as when the 26 was in. And if you go down to a 6 millimeter eyepiece, it's going to move twice as fast as when looking through the 12 or 10 millimeter eyepiece. So you're going to have to be moving this a whole lot more. By most, I mean well over 75%, probably 85% of all my astronomy viewing is at low power with a 25 or a 30 or maybe even a 40 millimeter eyepiece in a really wide field, really low power. I find that much more enjoyable than having to deal with something at really high power. And I have a telescope that can track and stay on the target. That's okay. I still like the low power. People get really, they crave that massive power. And, you know, our boxes don't say, you know, 800 power telescope. Yeah, if you see a telescope like that, don't buy it, because it can't do it, right? If it's a department store telescope, it can't do it. Can it do it? Sure, it can do it. Can you get the magnification? But it's not going to work because it's moving so fast, you can't keep what you want in the eyepiece of your telescope. Don't buy into that massive marketing. Why? Because those companies know how to market to you, and they know beginning astronomers think more magnification is better. But I can tell you right now, less magnification is where you should start, and slowly work your way up to understand what magnification does. Again, significantly more than 3/4 of my viewing. And when I do outreach, 95% of my outreach is at low power. Every once in a while, you know, if it's not a big crowd, and I've got a telescope mount that tracks, in other words, there's got motors that follows the object across the sky, I'll increase the magnification, but that is a rare day. All right, so here on Amazon Live, we'd love for you to reach out to us and say hi. And if you're new to the channel, click that follow button if you like the educational value that we're offering, as well as seeing some of these products right here. So I'm going to switch telescopes. What you got?
So Fiddlesticks. Hang on a second.
Looks like you're trying to get up a picture of a comet.
Yeah.
While you're doing that, I'm going to switch out the telescopes.
Issues.
And this is going to be an equatorial mount, so we're going to show you how to do a polar alignment here in a minute, because that's a skill you have to learn to use this mount.
There we go. Here we go.
Off into the wild blue yonder?
No, I'm doing something.
That scares me, Paul. Not really.
It's so... I can't seem to do anything right these days. Anyway, keep going. I'll get it.
He's trying to get a picture of a comet up. So anyway, all right. So this is the First Light series, 114 millimeter Newtonian. What that means is it's got an objective end. The previous one had an objective of 80 millimeters. This one has an objective end of 114 millimeters. It's going to collect significantly more light than the 80 millimeter telescope. But this is a Newtonian design. This has a mirror in the bottom, not a lens set. There's a mirror right here that's curved. Light comes in the telescope. Let me see how I can do this and get it to where you can see down the telescope. This is going to be, got an idea. How about that? There we go. So right here, you can see that there is a circle with 3 veins holding up. That's holding up a mirror. The light goes past that mirror down to the bottom of the telescope, which is, we'll turn it this way, to the bottom of the telescope where there's a mirror, right? That curved mirror, the light comes in, bounces off the curve, which is an angle, and starts coming to a point. That point is called the focal plane. So what happens is it's coming back out the telescope, right? Remember that mirror down there? It's reflecting it back towards the front, but it's getting smaller and smaller. It reflects off of a flat mirror that's right underneath the focusing unit and reflects that focusing light out the side, where now we can use the focuser along with the 25 millimeter super plossel this telescope comes with to get the object we're looking at into focus for our eye. Now, it may be in focus for me, but it may not be in focus for you, and it may not be in focus for the next people. So you got to learn to focus. Everybody's got to learn to focus the telescope to make it work. If you wear glasses to see distance, you're probably going to need to use them at the eyepiece. If you use glasses to read like I do, then you're not going to use those at the eyepiece. Probably experiment and see what happens. So this mount is clearly different than the mount we were looking at a while ago. That's because this is called an equatorial mount. Equatorial for equator. So what you want to do is figure out how far north or south of the equator you are. Here in northwest Arkansas, we are 36 degrees north of the equator. So right here on the side of the telescope, there's a little gauge that shows 36 on it, and we're going to move the telescope by turning. Let me unlock it a little bit. We're going to move the telescope. We can raise it and lower it right there. And what we're doing is we're getting this axis aligned with the rotational axis of the Earth, which is based on your latitude. That's how much higher or lower you need to make the telescope. Once that's done, you got that set, then you've got to figure out how to polar align. Well, polar aligning is a skill to learn. It can be done. Paul, you got the video ready?
No.
Well, I told you we're going to do a polar alignment and have the video.
I told you I was working on this.
Paul's going to get you.
I'm busy.
He's busy doing things that don't directly relate to what I'm talking about right now.
They do.
How about that?
All right. Fair. Here we go.
Hey, everybody. Kent Marts here from Explore Scientific. Today I'm going to teach you how to polar align your telescope using a broom. Why do you need to polar align? Well, with a telescope that has an equatorial mount, you have to get that equatorial axis lined up with the rotation of the Earth. And to do that, we're going to start with the tripod. We're going to decide which one of these legs is going to point north, and we're going to set the tripod down so that leg is pointed north. First thing I'm going to do is use a level to make sure my tripod is level So if it's tipped one side or the other, that's going to cause your polar alignment to not be accurate. So we're going to use a level for that purpose. Then we're going to take a compass, and just to make sure that I've got it pointed north, I'm going to use the compass, line up, and go, yep, that looks like it's pointed north. So here's what I'm going to do now. And this is where the broom comes in. The broom becomes a measurement device, if you will. So I'm going to put the broom on the ground with the tip of it right against the north leg of the tripod. And I'm going to back away, and I'm going to use the compass. I'm going to close one eye, and I'm going to use the compass to make sure that the broom is lined up with north, right? And so I can tell I'm off just a little bit. So I'm going to move the tripod just a little bit, and I'm going to turn the broom. And the broom is what I'm seeing that line with to line up. So closing one eye. Now my broom is lined up perfectly to magnetic north. Right here is we're going to talk about something called magnetic declination. The magnetic north is not true north. The difference between true north and magnetic north can be off by as much as 15 or 16 degrees if you live on the east coast or west coast of the United States. Around the world, it varies. And you have to figure out what that is for where you live. Because if you point at magnetic north, you're not going to be pointing at true north. You could be off by 15 degrees. Your go-to will never be accurate. So for this system to work, you have to know what that offset is and be able to program that into your compass. We're going to provide a link to a website and a video that talks about that a whole lot more. Now, we're going to make sure that the tripod is not angled wrong. I'm going to use a small tape measure, and we're simply going to come down here and be careful not to move the broom. And I'm going to measure the distance from the tripod leg to the center of the broom. That is 470 centimeters. That way, it is 470, a little, I'm going to call that good. Actually, I'm going to move the tripod a couple of millimeters, just like that. So now, we know that we're lined up true north with that leg, and these two legs are the equal distance from right here. So it's not pushed that way or that way. So now that we have the tripod with a good alignment to north, we have to put the head on the mount. And that's going to entail this. We're going to be very careful when we do this because we don't want to move the tripod. We're going to put it on and simply screw on the polar head just like this. Remembering everything's going to the north. Now if you're in the southern hemisphere, you're going to do the same thing. You can do the exact same in the southern hemisphere because it's not polar, it's polar alignment. We just don't use the star Polaris, which we're not using here. This is really good if you can't see Polaris, or if it's daytime and you want to do some solar viewing with a solar safe filter. So the last step of this process is to check the scale of your altitude, right? So we live at 36 degrees north, and I am going to turn the altitude until it gets to 36 degrees north. I'm going to stop. And that's it. With this system, using a broom, a compass, and a tape measure, you can achieve a good, decent starting polar alignment. Personally, I've used this, and I've got an amazingly close polar alignment. There's ways you can use to refine your polar alignment, specifically drift alignment, but it all starts with a good polar alignment. You can do this in the daytime. You can do this in the nighttime if you can't see Polaris. It works all the time. It's a good way to get started learning the process of polar alignment. Isn't that great? I hope you've enjoyed this video. For Explore Scientific, I'm Kent Marts. Get out there and start doing astronomy. And keep looking up. There you have it. You now know how to do a polar alignment to get it lined up with the north celestial pole, true north, rather than magnetic north. That's the key that a lot of people miss. If you use a compass and you live on the west coast or the east coast of the United States, the compass may point north as much as 15 or 16 degrees off. So you got to learn how to deal with that error right there. So we're going to assume we got the mount polar aligned now. And so here's how you use this equatorial mount. First off, it's got slow motion controls. This, remember the first one was just left, right, up, and down. You grabbed a handle, had to move it. This mount is a step up. It's got slow motion controls, and I can turn it real fast. You can see the telescope's moving right there, maybe. Yeah, there you go. You can see it moving right there, okay? And this one turns this axis. So let's talk about these different axes. This axis mimics the rotation of the Earth. This is called right ascension. Don't need to know why. Just understand that this axis is how mimics the rotation of the Earth. That's the polar axis of this mount. There's a little lock over here. It's a little knob you turn to keep it from turning by itself. Up here, this axis is called the declination axis. And it is sort of up and down, but not really. So if we want to look at something that's in the northern hemisphere, or in the north, say, we want to look at Polaris, we just put it straight down, and just like this, you should be able to see Polaris. If you've done a good job of polar aligning, you should see Polaris in the eyepiece. Let's say we want to go to Mizar and Alcor and the handle of the Big Dipper. Let's say that it's right there. So now we're going to find it with the red dot. And you can use a star atlas or a planisphere, and we'll talk about planispheres here in a minute, because we've got a planisphere over in the Amazon carousel that you can pick up as well. So let's say you've got this on Mizar and Alcor, and now you can simply just follow it all the way across the sky by turning the right ascension, right? And it's just going to follow that spot all the way across the sky. If you're off a little bit, it may drift in declination. Remember, this is the direct declination axis going this circle. You simply turn it and center it back up and figure out which way, where you need to go to get it positioned, so it'll stay in the eyepiece a long time. Harder to learn than the Twilight Nano, where you just set it down and just left, right, up, down, point the telescope. But the equatorial mount is more powerful. It's more powerful because, like I said, once you find the object, you should and have done a good polar alignment, and rough is good enough, especially starting out. You've got a good rough polar alignment, start using a telescope, right? And as you get better at polar alignment, you'll find that the the mount is easier to use. I said rough enough is good enough. Don't let the quest for perfection in amateur astronomy or lots of other things get in the way of good enough to start using your device. If you want to get everything perfect before you ever use it, you're not going to, because it's skills you have to learn, and you have to make little mistakes and learn from them to make you get better, right? And I've literally had people who've called in with problems and questions and situations and things they didn't understand, and I finally say, Have you used the telescope? And they'll say, no. I say, why not? Well, because of this and that and the other thing. I say, okay, so look, it's clear where you live tonight. Why don't you just go out and use the telescope tonight? No matter what, go out and use the telescope. Because I'm telling you, close enough is good enough. Go out and use it. And learn, enjoy it. See those beautiful things. See craters on the moon. See the rings of Saturn. See the planets of Jupiter move in front of your eyes. Yes, you can see. Did I say the planets of Jupiter? The moons of Jupiter. See the moons of Jupiter move in front of your eyes. If one of those moons is close to the edge of Jupiter, you can actually see it moving over 5 or 10 minutes. It's truly amazing to see something up in the sky that you can tell is moving. So I think we have a question coming in. There we go. What telescope could I get for €350? 350 euro is, that's not euro, that's pound sterling. Paul, would you do a 350 pound sterling conversion? So it'd be 350 pounds to USD. It's going to be like, I don't know what the conversion rate is. It may be 1-to-1. I think that maybe 1-to-1 right now. Just happened. Somebody's currency had gone to a 1-to-1. Paul is over there trying to find it on his phone.
That's something I do every day.
Just, hey Noah. No, can't hear me. And he can't do it on his phone.
I can. Try to do everything else too.
What you got?
Trying to do everything else too.
I know, but what do you got for the pound sterling?
350
pounds to USD.
Search.
Noah.
Pounds to dollars.
Search for pounds to USD. Pounds, like pound sterling, British money. Pound sterling to USD.
Well, it
350 pounds is how many dollars?
It's about 200 or
416. So 350 pounds.
416 US dollars.
So $400 conversion rate. I believe it'll get you all of these telescopes we're looking at right now. This telescope right here we have right now, the First Light
279,
114 millimeter Newtonian on the equatorial mount is $279.
It's like
now,
190 pounds.
Obviously, if you're talking about pound sterling, you're probably in the United Kingdom, Great Britain, England. You know, I know there's politics tied up in all of those, and I apologize for
Find it on Amazon.
Consternation.
And you'll get it from Bresser, Germany, I think.
I don't know if they have these or not, but a telescope like this, in this range, all the ones I've been talking about are going to be within your price range. You buy this one, you have money left over to buy a couple of other, at least one other 52-degree series Explorer Scientific waterproof eyepieces, and that'll still be really close or within your budget. What is the focal length of this reflector? It is 500.
That was the reflector, yeah.
Of this reflector, it's 500 millimeters. This is the Newtonian Telescope, named after the inventor of this telescope, the person who also invented gravity, not discovered gravity, described gravity, talked about gravity in modern terms. Sir Isaac Newton came up with this design of a telescope because refractors were getting so long. He came up with a way to get to shorten up the focal length and make them much more user friendly. So Sir Isaac, Julian, but that's just my opinion. Honestly, trying to find a local star group will be very helpful. Yes, Osmosis 007. I'm not sure what Julian said, but if you can find a astronomical society, an astronomy club, whatever, in your area, most assuredly, like learning any other hobby, it's much easier for you to have somebody, a mentor, to teach you how to do it. Kent equals facepalm.
I have no idea. Something you said.
Probably the planets going around Jupiter. I'll bet that's what it is.
Well, they could be planets if you were something else.
Yeah, I'm going to guess that's what that was about. So, yeah, there we go. All right, so...
with this, you could just go out and plop it down and possibly see the comet.
Yeah, there's a comet, Pan-STARRS 1307 K2 or something like that.
Yeah.
Yes, that you go out and see. I believe it's in the constellation Ophiuchus right now, which is in the southwestern sky. The problem is that tonight the full moon is very, very bright, and it's going to make it very difficult to see that
in
comet.
The northern hemisphere, you should be able to see it until late September.
So my advice is to not try and see it tonight necessarily, unless you're just dead set on looking at the full moon and then looking for the comet. Wait 3 days or 4 days. 3 days, the moon's going to come up well after sunset, giving you time to get the sky get dark and you see Ophiuchus up in the southwestern sky.
Do you think it'll look anything like some of the ones in the past once the moon go away?
From what my Sugar Creek Astronomical Society friends were saying, if you remember Comet Neowise a couple of years ago.
Or Hale-Bopp.
Well, okay, no, it's not going to look like Hale-Bopp. It will not look like Hale-Bopp.
Because that's what I have loaded. That's why.
It's not going to look like that. And again, you have to remember that this is taken with a camera, right? So it's a long exposure. You can tell it's a long exposure because the stars have moved. No, have they moved on that one? Nope. They maybe
it says right there, doesn't it?
It was taken with a telelens, so we know this person is probably not American. The dust tail fans out to the right while the bright, well-separated blue ion tail is pointing straight away from the sun. Chances are this was a tracked photograph. It doesn't say how long it was, but it doesn't take very long for the camera to build up light. You gotta remember, your eye is operating about 1/40th of a second. That's why if you're looking at a light and it's not flashing, and you're in the United States, you're on 60 hertz, that light bulb is flashing 60 times because your eye stays open too long, right? If it was a shutter, so you can't see it. So you're really only seeing 1/30th of a second exposure of what's coming into your eye. So if you have a 5-second exposure, you're building up on the sensitive camera.
There's some debate over that.
Okay, whatever it is, it's operating slower than 1/60th of a second.
Well,
because it was faster than 1/60th of a second, Paul, you could see the lights flash, and no one can.
Not necessarily true, because if you're going 120 frames a second and you're watching it in real time, or even 200 frames a second, it happens so rapidly you don't see the lights flash.
Correct. That's what I'm saying. It's happened so fast you can't see it. However, if you've ever been watching a sporting event where they go in slow motion, like real slow motion, and you can see the frame getting brighter and dimmer, looks like it's pulsing, you're actually seeing the lights flash on and off. You're actually seeing that flash because the camera is going so much faster than the light is, and they play, a half a second of action takes 20 seconds, you're seeing those lights flash on and off.
What's the fundamental difference between the two telescopes we've seen so far?
One's a reflector and one's a refractor. One's like Captain Jack Sparrow's spyglass, or the telescope Galileo used, got to use to observe the heavens. That's what he really did first. He improved the design of a previously existing telescope, and he used it to look at the heavens. So one's a reflector and one's a refractor. One refracts the light into a point. This one reflects the light into a point.
So they have better uses. There's the right, like you said, the right tool for the job.
So there's different kind of hammers, right? There is no perfect telescope, just like there's no perfect hammer. If you're wanting to drive tacks, the perfect hammer is a tack hammer. Can you do it with a jackhammer? Yeah, if you just set the jackhammer down on it and don't turn it on and turn the air on, the pneumatic hammer. If you're wanting to split wood and beat on a wedge, a splitting maul or a 9-pound sledgehammer works well. If you're wanting to frame a house, a framing hammer is the tool to use. If you want to roof a house, a roofing hammer. They're all hammers. Heck, I've driven nails before with a pipe wrench, right? Because it's the only thing I had that would work, so I used it. The point being, there's tools for jobs, right? Every telescope is a balance. There's no perfect telescope that'll do it all. A refractor offers high contrast views. A Newtonian offers a whole lot of aperture for not a whole lot of money. Aperture, the 80 is this big, the 114 is this big. You get up to 127 millimeter refractors, 152 millimeter refractors, 5 and 6 and inch refractors. They start gathering more light. Because they don't have this central obstruction, they offer higher contrast. Now, eyepieces can change the contrast, but this nice short tube makes it really nice. And this is a Newtonian telescope. I don't have one here because we don't have any in stock, but and we're getting ready to in hopefully a couple months. Excuse me. They're called Dobsonian telescopes. They're a Newtonian telescope on what amounts to a lazy Susan and a couple of vertical
we've got
boards
them in the showroom.
With yeah, you can show them with some curves cut in, so it's easy to use. Those telescopes, 6, 8, 10, 12. We have one that goes up to 20 inches in diameter. That's the big boy telescope. So Paul's getting up a picture of a Dobsonian telescope. They're called Dobsonians because after the monk in San Francisco, John Dobson, who really popularized that kind of mount. Literally, you just turn it left and right and raise the telescope up and down. It's just like that Twilight Nano I showed you earlier, just designed a little bit different, right? So, what you got?
You're just going to...
Okay, so I thought you had something ready to go. Okay. I thought I saw it queued up. So I thought you had it queued up. So, beginners, for the bang for the buck, a Dobsonian telescope is one really good option. They can be bigger and harder to transport, which presents problems. If you have trouble lifting stuff, that presents problems too. Like I said, everything's a balance. You got wants and needs. You've got budget and expense. You've got eyepieces. There's all sorts of other kit you can get as well. That's why a kit like this, to get you started out, comes with everything you need to get started and then lets you get on down the road and figure out what you like. Again, somebody mentioned an astronomy club. If you can find an astronomy club, absolutely you should start going to those meetings and meet up with a buddy. Now, this is
the big boy.
This is the 20-inch telescope, Newtonian. It's a truss tube model, so it comes apart and packs up in a really small package. But a lot of entry-level Newtonians have a solid tube. Think of a pipe 12 inches or 10 inches in diameter.
That's a big boy there.
That's 20 inches across. That's almost 2 feet in diameter. That's a big telescope. But they all sort of look the same. You can't get the scale of... The cage on that thing is literally this big around, right? You can't really get that scale.
That's the same
it's the
stage
same everything. Yeah.
that Kent was standing on when we does the how to polar align.
Yeah.
So you can imagine it's the size of a person when it's put together.
It's really big. Yeah, I could come close to getting down inside of that. I wouldn't want to, but you can. Anyway, but a 10-inch or an 8-inch or a 6-inch Dobsonian telescope, it's going to be a solid tube, and it's going to be a tube about yay long. So if you don't, yay long, really long, maybe this tall, so it doesn't collapse down on those entry-level scopes. They're less expensive than these truss tube Dobsonians that you see. However, they can be hard to transport. You've got to have a car big enough, either a back seat that's wide enough or the ability to fold a seat down and stick it out through the trunk into the back seat to transport it. Once again, there's trade-offs for everything. Ken N, does the reflector require a coma corrector? This telescope, there's no real way to hook a coma corrector on to this telescope. The reality is the corrector would cost more than the kit does. Coma doesn't bother me. If I look at it, I can see it, but I ignore it. Coma or field curvature is caused by a curved surface, when the light starts hitting a flat surface like a mirror, like a camera sensor, that light comes in and it hits here and then it smears. And when it smears on that flat surface, it creates little spikes that are called coma, because the French thought it looked like comets, and the French word for comet is coma, and so they named it coma. So field curvature or coma are much the same thing. One's in a refractor, one's in a reflector. If you buy this telescope and you've never looked at a telescope before, you're not going to notice it. You might notice it, but the human eyeball is also a curved surface, right? And so your eye and mind work together to deal with those issues.
Every day at 1:30, Tariq.
Yep, every day at 1:30, unless we're running behind. And then if we're on...
2 o'clock on Amazon.
Yeah, 2 o'clock on Amazon, and we're on till 3 o'clock or thereabouts. So your eye does a miraculous job and your brain does a miraculous job of fixing the coma. Some people see it, and it really bothers them, but those people are almost always people who are experienced observers, and they've learned to see it, right? Or they have OCD, and it just bothers them because they know it's there. I fully understand and appreciate that situation. There's little things my OCD kicks in on, and I'm compelled to do things. And I'll be honest with one of them. I've talked about it, made no secret of it, talked about it on social media. I eat things like M&Ms and Skittles in units of 4. I also, Christopher Hughes, just stumbled into this, going back to the beginning to catch it all. Hey, Christopher, thanks for joining us. We're here, social media launch at 1:30, and then roll into Amazon Live at 2 o'clock. And this is a Amazon Live broadcast going out on, the feed. So we do a lot of education, talk about products, and you'll hear me say over in the carousel, that is a product on Amazon Live where you can click on and buy the products we're talking about. What a finder really do for me, Tariq. Not sure the question, Tariq. Tariq's in the UAE.
Why would he need a finder?
Why do you need a finder? Finding something in the sky, even something like the moon, can be a very large challenge. I was using an ED80 2 Fridays ago at a community festival that I go to, and was trying to find the sun manually. And I did it by having somebody stand down from the telescope, and I sighted along the telescope and had the sun directly above her head. And then my brother was there, and he was watching the shadows and everything. And we finally found the sun, but it took a couple of minutes to do it. Whereas if I would have had a solar safe finder, I could have done it in a few seconds, right? So finders, whether it is the red dot finder that comes with it or an add-on finder, like over in the carousel, you're going to see our ES Reflects site, and it's a heads-up site that projects 3 circles onto a piece of glass, much like this red dot is projected onto the front lens element here. It's a 0 power. It's really sharp how it works.
Going to have to find that thing.
We had one in here in the studio, and
it's
gone.
Supposed to be with me.
Yep.
It was in my orange box.
And it's gone. We can't find it. Nobody fesses up.
Also, I'm missing a extension tube.
It's amazing how things that are made of metal grow legs. It's weird. It's like if you pop accidentally pull the tail off of a lizard, it grows a new tail. Tariq, I never have any issue finding anything in the sky without a finder. I can even manually, I can go to. So what the finder is really helped me for. If you can find those faint fuzzy things up in the sky, Tariq, you don't need a finder. It's a skill you've developed, and great for you to be able to do that.
I can do it too, and it's not something that I've trained for. My brain understands how to point something
mine
at
does too,
the star, and I can do it every time.
Mine does too, but I'm trying to find the sun with a solar filter on it.
But not everybody can do that. That's just
everybody has
talent.
Talent. I was going to say everybody has a skill that they are very good at.
Yeah.
So while we're talking about me trying to find the sun to look at, let's talk about looking at the sun. If you have a telescope, don't do it. Period in the story. Don't do it until you learn how to do it safely. And one way of doing it is with the Explorer Scientific Sun Catcher, large aperture, solar filter. This thing right here is made out of Thousand Oaks film. It comes shipped, put together, folded together. It's cardboard. Has the Thousand Oaks film, highly reflective, reflects well over 99% of the light away from the telescope. Doesn't build up heat. It's got some internal coatings in there that make it a pleasant yellow-orange glow like the human eye really likes. On the back side, you'll have 4 pieces of double-sided tape that are separate. You're going to peel off one side and stick it on here. And once that's done, you're going to take the 4 pieces of triangle foam and pull it off the tape and stick it on here. Well, the foam in here has been used so much, these won't stick on anymore, but you get the idea, right? And so you're going to stick them on there, and there's going to be 4 of them. And then my advice is you take the lens cap, right, and you press it down in there just like that, and you mark the plastic. Look where the little mark is, and then take a regular knife. And, well, actually how I do this is before I stick them on, I put them in there because I don't want to cut the film, right? So I put them in where I'm going to use them. I put this on here. I mark it. I cut inside of that line. I want to make sure I have a nice, tight fit when we put this up on the telescope, right? We don't want this coming off. We want to have to work this on and squeeze it on there. If it just goes on there, like, then you have it too loose. You need to contact us and get new ones of these so we can get you fixed up. And once I have it sized correctly, then I am going to pull these out, pull the double-sided tape off the outside, stick these 4 in place, and off I go. Now, this is going to mount right there on the front of the telescope. Now we can safely look at the sun with this Newtonian telescope. Lining it up, I just line up the shadow until the shadow gets really sharp and crisp on the ground, and then I look through the telescope, and most of the time it's there, or I can adjust it and find it using the slow motion controls. That's all there is to it. We make these for every size of telescope. We don't make one for the 20-inch Dob, although I guess we could if we wanted to. But yeah, we could engineer one for you. But very inexpensive, yet very effective and very functional. Why would you want to look at the sun? Well, there's an 11-year cycle in the sun called the solar cycle. And it goes from having no sunspots on the surface of the sun to having a whole bunch to having none. That's an 11-year cycle. Right now we're coming out of solar minimum. We had for a couple of years with effectively no sunspots, just a big round disk in the sky to look at. Now we're seeing more and more and more. Right now there's some sunspots that are naked eye sunspots. If you have solar glasses, you can go out and put your solar glasses on, look up at the sun, and see the sunspots on the surface of the sun with no magnification. With magnification, wow, looks fantastic. With just a little magnification, you can go more and more, and if you have a tracking mount, follow just individual sunspot areas. What's a sunspot? I heard you ask that. Somebody, I heard who it was, couldn't tell whose voice it was. Sunspots are areas on the sun where the magnetism gets all twisted up. So on Earth, there's a molten core that creates a magnet. And, you know, the poles are just like that. The magnetic lines are well organized. Don't get mixed up. On the sun, there's no molten core that's creating the lines of magnetism like on Earth, and they come out all over the place. Well, sometimes they get all twisted up and tangled. Where that happens, it holds back the production of light, and that area cools off a little bit. Now, cool is relative, friends, because, you know, the surface of the sun is 9,500 degrees, you know, and the sunspot is 6,000 degrees maybe. So it's significantly cooler, but if you're standing next to it, it's still going to vaporize you because it's still super duper hot. Now then, if the sun was just as bright, if the color of the sunspots was all over the sun would still be extremely bright. It's just that these filters cut it out and make it look dark when it's still producing a whole bunch of light from that spot, just not as much as around it. The sunspots move, they grow, they change. You'll be sitting there watching the sun, and I've done this for hours, sitting at the eyepiece just watching, and you'll notice one area starts looking a little bit disturbed or funny, and you keep watching it, and you're like, is that turning dark? And over the period of 15, 20 minutes, a sunspot starts growing, and in a little bit you can see, yes, really is a new sunspot right there. And sometimes they die out. Sometimes they become really big sunspots and grow over time. Some spots, and if you look at the sun, there's two bands where the sunspots are most prominent, and those bands rotate around. Some spots are so big and last so long, they'll go a couple of revolutions on the Earth-facing side, so we'll be able to see the same sunspot a couple of 3 times until they finally die out. But going up into solar maximum over the next couple of years, there's going to be more and more and bigger sunspots. And you most assuredly want to be ready if you're in North America or Central America. You want to be ready for the solar eclipses coming up. There's an annular eclipse in 2023 and a total in 2024. You want to be prepared for that. You want to start learning how to use your telescope to look at the sun. You want to start learning how to photograph the sun with it. Like anything else, there are people who buy a telescope and it gets delivered today and they want to go out and look at the moon tonight. They may do it, but they're not going to have the pleasure they would otherwise, because they're going to be, especially if they've never used a telescope before, they're going to be out there struggling to make the telescope work. It's going to be very frustrating. That's really not the way to do it. You got to start getting ready for things like that way in advance. So, all right, rolling up on 3 o'clock here on Amazon Live. If you are watching us out there in Amazon Live land and have never clicked that follow button and you like what you're seeing, the education we're doing, we would be honored to have a follow from you. We appreciate it very much. And that follow helps the Amazon algorithms. The more that people follow us, the more people get served our content without having to stumble on it, and that's a good thing, because we try really hard to do a lot of education, not just push product. So today's Wednesday. Tomorrow we're going to have On the Wing. We'll be talking about birds and birding and things like that. Friday will be First Light Chronicles, and roll back into Monday, where...
Friday is Focus on Astrophotography.
What'd I say? Yeah, okay, Focus on Astrophotography is Friday. And then we roll into next week's programming. We try to go live on Social Stream at 1:30 and then on Amazon Live at 2. Go for an hour, and there you go. So, on behalf of Paul Newton over in the control booth, thank you, Paul, for your work today. Noah Menard, Marketplace Menard, over keeping the Amazon and other platforms up and running and current and correctly priced and inventory correct. And everybody else here in the Explore Scientific family in Springdale, Arkansas, I am Kent Marts. I bid you a great day. Thank you for blessing us with your time. Bye-bye, everybody.